Yes, it's another year, another PiDay. All right, so welcome to Math 150, Section 2, Lecture probably 17. So what I want to do today, since there's an exam coming up, this is not the greatest time to do a huge amount of new material. So what I want to do is I want to cover some stuff which you should hopefully have seen in earlier classes, but may not have, that will allow me to review material we've done this semester. Okay? And then with whatever time is left over, I'll just open it up to whatever questions you have on material. How many of you have seen a proof that the area of a circle of radius 1 is pi and that its perimeter is 2 pi? Okay, this is something we really need to know. These are fundamental constants. Now today is PiDay, it's March 14th. What time should the celebrations really kick in at? 3:14? No, not 3:14. 2:59. Approximately 2 o'clock, 1:59. Right, 3.1415926. If you want to get exactly what second, you should begin your celebration. One of my professors, I don't know if CirclesReview was the first one to say this, said if the Greeks were really intelligent, they would have discovered not pi, but 2 pi. So the real question is, what is the fundamental constant? Is it the area of the circle, or is it the perimeter? How many of you are thinking about doing more physics? All right. So you might see the electromagnetism constant, the 1 over 4 pi epsilon naught. Where does the 4 pi come from?
Isn't it the same thing as the constant? 8.89.
Yeah, but why do they have a 4 pi? Because they have your 4 pi epsilon naught. Why the hell are they writing it like this? Why not incorporate the 4 pi into the constant? Bless you. Anybody know something related to a circle that has a 4 pi? Sphere. So what part of the sphere? What quantity associated to a sphere has a 4 pi? Not the volume. Volume is 4/3 pi. So it's the surface area. The surface area is 4 pi. So there's a lot of different constants that you could argue are fundamental, and then the other ones come from them. So I want to go back to the area and perimeter of circles. So a lot of this goes back to Archimedes, this goes back thousands of years, this goes back to time before calculus and before really good systems of numbers. So it's absolutely amazing what was done. So the first thing I'm going to ask you to basically decide whether or not you will give me as fair game is that a circle of radius 1 has a well-defined area and a well-defined perimeter. Do we all accept that as a reasonable starting point? If not, we've got to really roll up our sleeves and start going back to the very foundations of mathematics. But if you're willing to accept that a circle has perimeter, great. Then we can do a lot from there. So let's start off with a circle of radius r. And then watch carefully for mistakes. I may make mistakes. Right? One way to try to calculate the area and the perimeter is to inscribe regular n-gons and circumscribe regular n-gons. And then everything on the inside should hopefully be a lower bound, everything on the outside should be an upper bound, and hopefully they'll converge to a common limit. What does this remind you of? Yes? Fundamental theorem of calculus, the Riemann sums, the upper and the lower sums. This is a way to review this idea. What we could do is we could start off with a regular 3-gon, then a 4-gon, then a 5-gon, etc., etc., etc. Or what we could do is we could start off with a regular maybe 6-gon, and then subdivide all the sides, and then subdivide again, and subdivide again, and subdivide again. This is similar to the issues we had when we were doing partitions. It's sometimes easier to just divide in half rather than go to the very next one, because if you go to the very next one, you have to start all over from scratch. So explicitly, if I take a hexagon, this is hopefully a good approximation for the area and the perimeter. If I now divide and double the number of points I had, so here were my original points, I now add one more point in between each one of them. It's getting hard to see the difference between this and the circle. And you can see that the area is getting very, very good. And then as I do more and more points, the area is going to get closer and closer and closer. The area will converge. And we hope the same is true about the perimeter. Perimeter is a little bit more subtle because things are curved, but it does look like we're getting a better and better approximation for that shape. And there really is a well-defined value for the perimeter of a unit circle. So what we can do now is we can now calculate, say, what happens at the nth stage. So here is my arc of the circle. Here's my radius r. And now I have to decide what units I want to measure my angle in. What are two good candidates? Radians and degrees. Why are degrees a good candidate? But why are degrees a good unit to use? Why is...
Because radians are in terms of pi, figure pi.
Well, so we don't yet know exactly what pi is. It turns out radians are the better units. Why do we like degrees? Yes. I'm sorry? So it's close. I mean, we're basically used to these numbers. You know, the Babylonians loved 60. 60 has a lot of different factors. How many of you have ever used a computer keyboard? It starts off QWERTY. Why do keyboards start off? Yeah, on old typewriters, they would jam if people typed too quickly in quick succession. So the typewriter people deliberately chose the order of the letters to slow you down. And we're just stuck with that. You know, there's a lot better keyboards for professional typists. We're not going to change. It would require one generation to suffer so that their children could have a better life. And we're just not nice enough to do that. And when you get older, you're not nice enough either. But eventually everything will be audio, so it won't really matter too much. But you're sometimes stuck with things. We're stuck with degrees because that's what we're trained with from an early day. But degrees is not the right units to look at. It has some issues. For now, I'll just call this angle theta n, and I'll call it theta n over 2. I'll be a little bit unclear right now. So let's calculate this triangle. I have a right triangle, and so if this is the hypotenuse is r, this side over here is going to just be r sine theta n over 2, and the base of the triangle will be r cosine theta n over 2. And so now what I can do is I can calculate the perimeter of my n-gon, and I can calculate the area. So the perimeter is going to be, I have n triangles. Each one of them is r sine theta n over 2. And the area, I have n of them, is going to be 2 so it's 1/2 base times height. So it's going to be 1/2 base, which is going to be cosine theta n over 2 times the height, which will be, and that's an r, times r sine theta n over 2. So are these correct, or did I make a small mistake somewhere? So to calculate the perimeter, I have a height of r sine theta n over 2, and I have n of them, so it's n r sine theta over 2. And to calculate the area, it's 1/2 base times height, so it's 1/2 base, which is r cosine theta over 2, times the height, which is r sine theta n over 2. Yes? The height is 2. Right? The height is not just the top part, it's also the bottom part. So when I'm calculating both the perimeter and the area, I need to remember it's twice that. All right, so I have a formula for the perimeter, I have a formula for the area. I'll just rewrite these a little bit nicely. Pn is r times 2n sine theta n over 2, and an is r squared times the 2 and the 1/2 cancels, it'll be n cosine theta n over 2 sine theta n over 2. Let's look a little bit and see what happens as n gets very, very large. As n gets very, very large, this angle is going to go to 0. So what's the cosine going to go to? So the cosine of 0 will go to, it'll go to 1. And what will the sine go to? Sine will go to 0, but I have an n over here, so the n is going to be competing, because the n goes to infinity, this goes to 0, and the cosine is just watching harmlessly. Similarly over here, the n and the sine of theta n are going to be going in opposite directions. I could actually rewrite this. We have a formula for the sine of theta n over 2 times the cosine of theta n over 2. Anybody remember their trig identities? So this is the same as r squared times, if I put in a 2 and a 1/2 n sine theta n. So the sine of 2x is 2 sine x cosine x. That's one of our trig identities. 2, so I'm using sine of 2x is 2 sine x cosine x. And what's nice about that is now everything here just involves sine. Unfortunately, a huge amount of all of mathematics is dealing with algebra and trying to write things in good illuminating ways. So let's look at what we have over here for the perimeter. I'm going to write the perimeter as 2r sine theta n over 2, and I'm going to put the 1 over n downstairs. So if you think, if I multiply by n over n, the n will cancel the 1 over n down below, and that's the same as this expression. I'm trying to make this look a lot like the limit that you see when you take the derivative of sine. It should be the sine of h minus the sine of 0 over h. It's not quite the same. I have theta n over 2 and I have a 1 over n over here. But theta n, that should be the total angular measurement divided by n. So it's at least somewhat similar. For the area, I will have r squared times 1/2 times the sine of theta n with a 1 over n down below. So there's a couple of things that are worth noting. The area is a two-dimensional object. And I see that it depends on the radius squared. So if I double the radius, the area goes up by 4. If I triple the radius, it goes up by 9. It behaves as we would expect. If I look at the perimeter, this is a one-dimensional object. It depends linearly on the radius. If I double the radius, I double the perimeter. So there's a lot of really good things about this formula. What it also tells us is that we really only need to understand the unit circle. If I want to pass from the unit circle to a circle of radius r, multiply by r squared for the area, multiply by r for the perimeter. So we really only need to understand what's going on for the unit circle. So there will be some quantity. The unit circle will have some area. It will have some perimeter. So let P be the perimeter of the unit circle. In your mind, what should you be thinking right now? What value should you be thinking? I'm sorry? When we're talking about the perimeter of a unit circle, a circle of radius 1. So what is the perimeter of a circle of radius 1? 2 pi. So we should be thinking in our minds that P equals 2 pi. What we're going to do now is we're going to choose our angular measurement so that the number of angles going all the way around is equal to the perimeter of the circle. And the advantage of that is now basically the arc length of a unit circle is equal to the angular measurement of the arc over here. If you think about, a quarter circle, well, if the whole circle has circumference 2 pi, the length of a quarter circle would be 1/4 of 2 pi, also known as pi halves. And what's the angular measurement of a right angle? Pi halves. This is why we use radians. When we use radians, the angular measurement is equal to the length of the arc on the unit circle. If we had a circle of radius r, then the length of the arc would just be r times the angular measurement. That's the advantage of using radians. So now, P is going to be the perimeter of the unit circle. So theta n will just be our perimeter divided by n. So the nth perimeter, our approximation, is going to be 2r, and then we have the sine of theta n divided by 2. So that will be P divided by 2n divided by 1 over n. Yes?
What happened to the sine of theta n over 2 for the area?
For the area? This is the area, right?
Yeah.
What are you looking for? What's missing?
What happened to the 2? So it's sine theta n over 2.
Oh, no, because we had cosine theta n and sine theta n over 2. Both of them were over 2. So when we used the double angle formula, this became the sine of twice theta n over 2. So that became these two with a factor of 2 combined and gave us that.
Okay.
And that's where the extra half comes from. Because for the double angle formula, we wanted to have double. Okay. All right. So now, looking at what we have, what would you rather have on the bottom? You don't want to have 1 over n. What would you rather have instead of 1 over n? I'm sorry? Well, look at what we have on the top. We have the sine of p over 2n, and on the bottom we have 1 over n. What would you love to have on the bottom? Not 1 over n. I'm sorry? 1 over 2n is closer, but not quite right yet. Not into the negative 1. When we do trig, we would do, the sine of h minus the sine of 0 over h. That looks a lot like that, but not exactly. What should the denominator be? It shouldn't be 1 over n. Look at what we're taking the sine of. The argument is p over 2n. We want the denominator to be p over 2n. Because then it's going to look like the sine of h over h. It'll be our derivative from calculus. So if we want that, we have to multiply by a p halves down below and a p halves up top. And now, the 2 cancels the 2 there. I'm sorry, the 2 cancels the 2 here. And we're doing radius equals 1 now. And so now we would just get, the 2 cancels that 2, we'll get p times the sine of p over 2n divided by p over 2n. And this will be the nth approximation to the perimeter of a unit circle. Okay? As n gets very, very large, what should this converge to? Well, we don't know 2 pi. What should it converge to? What have we said the perimeter of the unit circle is? What are we calling the perimeter of the unit circle? P. So what does this have to converge to? This has to converge to P. P is fixed here. So what do we know about this limit? This limit is what? Has to be 1. So the sine of h over h, we got into trouble earlier this year when we used L'Hopital's rule to take the derivative, because we didn't know that the derivative of sine was cosine yet. This limit is 1. And that will give us that the perimeter of the circle is P. All right now we don't know the numerical value of P, but we at least know that things are consistent. Now that we know that, we can now pass to the area very easily. So we have a formula for the area. The area is I equals 1. So we get the area is just 1/2 the sine of theta n is just p over n divided by 1 over n. What do we want to multiply? What do we want to change the denominator to make this limit easier? Yes? Oh, we're doing I equals 1.
Okay.
We're just doing the unit circle at this point. So what would we want the denominator to be here? We want it to be p. So we multiply by p over p, and we get p times 1/2 times the sine of p over n divided by p over n. what does that limit go to? Right. And so what does just this part go to? 1. Have we proven that? This is where I would like security guards to protect me from you rushing me from being too theoretically rigorous. When we did this analysis here, notice we did the sine of p over 2n divided by p over 2n. We technically did this only dividing by even numbers. N could be odd. Maybe only the even values converge. Well, if that's the case, we could just go through our entire argument again and then just only calculate the area when there's a even number for n. But this goes back to, if the limit exists, it should exist no matter how you approach it. And we do know that the limit has to exist. The area has to exist. So this limit should be the same as that limit. If you're uncomfortable about that, then you can just go back and just double n over here, and then you'll be in this case. But this goes back to what we were talking about with limits earlier in multivariable, that it's not enough to approach along lines. The limit must exist along any path. But if the limit exists, then you can compute it by taking any path. So this limit is 1. So as n goes to infinity, an converges to 1/2 p. And if you're thinking that p equals 2 pi, then you would get that the area is pi. So we've now almost calculated everything we need to completely celebrate PiDay, right? We know the perimeter, if it's p of a unit circle, then the area is 1/2 p, and we know the r squared and the r dependence. All that's left is we need to calculate now the actual value of the perimeter of the unit circle. So how many of you have ever calculated the perimeter of the unit circle? You will do that now. You could, of course, approximate the perimeter by just looking at these n-gons and looking at their areas, and that will give you approximations. And the more sides you take, the better approximation you will get. I'm going to give you one of my favorite formulas for pi. So this is the Gregory-Leibniz formula. And again, it will allow me to review some good stuff from the semester. I am divinely inspired, and I choose to integrate from 0 to 1 the function 1 over 1 plus x squared. Perfectly nice function to integrate. When x equals 0, it's 1. When x equals 1, it's a half. It's a nice function. Does anybody remember the antiderivative of 1 over 1 plus x squared? Arctangent. So this is arctangent of 1 minus arctangent of 0. All right. What angle has a tangent of 1? Yes. Pi over 4. Could I write 45? So do I write pi over 4 or do I write 45? I write pi over 4. The reason is, as soon as you start to use the derivative of sine as cosine, you have now used the limit of sine of h over h as 1. So if I want to calculate the limit as h goes to 0 of sine of h over h and have that equal 1, that is only true in radians. If I take this physical angle and I change it to degrees, I have a scaling factor of 360 over 2 pi. The arc length here hasn't changed, but the angular measurement in here has changed. And so I will get a different value for this limit. This limit is only 1 in radians. In degrees, it's different. And so if you're doing anything with differential or integral trigonometry, you must always measure in radians. So this is pi over 4. What angle has a tangent of 0? Yes? I'm sorry? Not pi over 2. Because if you do pi over 2, tangent is sine over cosine, so you get 1 over 0. So pi over 2 would actually have a tangent of infinity. It's 0. So if you do 0, sine over cosine would be 0 over 1. So we get arctangent of 1 minus arctangent of 0, which is just pi over 4. All right, so technically I will only calculate pi over 4 for you. I will leave as an exercise calculating pi from what we get. All right? I want to rewrite this integral in a slightly different way. 1 over 1 minus negative x squared same integral. I'm only going up to 1 minus epsilon, and then I'll let epsilon be a small number going to 0. And so as epsilon goes to 0, this integral should converge to that. In order to make the argument that follows rigorous, I need to stop a little bit before 1. So much of this class, so much of life, sadly, is pattern recognition, and taking something and rewriting it in a way that will be more transparent. Does anybody recognize 1 over 1 minus negative x squared as something we've seen this semester? We've seen something like this before. Any thoughts where we've seen this? What if I gave you 1 over 1 minus r? Where have you seen 1 over 1 minus r as the answer for something? The geometric series. So the question you need to ask yourself is, why are you able to recognize it when I write it as 1 over 1 minus r, but not when I write it as 1 over 1 minus negative x squared, or even better, 1 over 1 plus x squared? You've got to get to the point where you can look at an expression and see all the different ways of relating it to something you've seen. Was I talking with your class about the different tables of integrals at the start of class today? When I was in college, we had to have 2 tables of integrals. A monster mammoth one we kept at home, and a small portable one so that we would always have the certain integrals available. A huge part of table of integrals is knowing how to use them. They can't write down every single integral. What they can do is they can write down a specific form. And then if you have an integral, you have to see, can I convert it to one of the forms in the book? If I see an algebraic expression, how do I convert this to something I know? And you have to realize, whenever you see something of the form 1 over, you should be thinking maybe it's a geometric series. And so if I write it like this, I can now say that this is the same as the integral from 0 to 1 minus epsilon of the sum, and goes from 0 to infinity, of negative x squared to the n dx. And now what I want to do is I want to switch the order of the sum and the integral. So this is the Fubini theorem. So you often do 2 integrals, a double integral, 2 sums, or a sum and an integral. And the question is, when can you switch? And the answer is, if the integral of the sum of the absolute value is finite, then you can switch. So what I'm going to do is I'm going to first compute, and then I will show you later that the integral of the sum of the absolute value was finite and everything was justified. So let's assume for now we can switch. So this is the sum, and goes from 0 to infinity, negative 1 to the n, integral from 0 to 1 minus epsilon of x to the 2n dx. All right. What function has derivative x to the 2n? So what function has derivative x to the 2n? X to the 2n plus 1 over 2n plus 1. So we have n goes from 0 to infinity of negative 1 to the n over 2n plus 1 times x to the 2n plus 1 evaluated at 0 and 1 minus epsilon. All right, evaluating at 0 is pretty easy. And so we now get the following. We start off when n equals 0, we get 1 minus epsilon minus 1 minus epsilon cubed over 3 plus 1 minus epsilon to the 5th over 5 minus 1 minus epsilon to the 7th over 7 plus dot dot dot. So that is the value of this integral. Does this sum converge? So one of the things that might scare us is we have small denominators, 3, 5, 7. If you remember the harmonic series from earlier this week, 1 plus a half plus a third plus a fifth, 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, that diverged. If we just sum the odd terms, it diverges. Now, we are lucky that we have minus signs, plus signs alternating that will help us with convergence. But the real thing that's saving us is we have higher and higher powers of 1 minus epsilon. And so let's look at the sum of the absolute values. So if we put in the absolute values, if we didn't have the negative 1, that would make the sum significantly larger. Let's see what would happen in that case. So let's investigate the sum of absolute values. So we would then have 1 minus epsilon, let's see, plus 1 minus epsilon cubed over 3 plus 1 minus epsilon to the 5th over 5 plus dot dot dot. This is less than equal to 1 minus epsilon, 1 plus 1 minus epsilon plus 1 minus epsilon squared plus 1 minus epsilon cubed plus 1 minus epsilon to the 4th. I'm being really careless. I'm dropping all the denominators and I'm adding in the even terms. So this goes back to when we proved the fundamental theorem of calculus. Sometimes all we need is for something to be bounded. We don't care what that bound is. That bound will affect how rapidly something happens. But if I just want to know something happens, I can be a little bit careless. And I'm trying to make my life as easy as possible. If I can't do the calculation, then I will roll up my sleeves and I will try to be more clever. But if I can get away with a cheap estimation, I'll do that. Does this series look like anything you've seen before? What does this look like? What kind of series is this? 1 plus 1 minus epsilon plus 1 minus epsilon squared plus 1 minus epsilon cubed plus 1 minus epsilon to the 4th. We've seen that today. It's the geometric series. So this is just equal to 1 over 1 minus the common ratio, 1 minus epsilon, which is 1 over epsilon. If epsilon is damn small, this is damn large, but finite. All that matters is that this is finite. And so because this is finite, this then converges. And the interchange is justified. And so if we look at this, this is an approximation to pi over 4. As epsilon gets smaller and smaller and smaller, this becomes a better and better approximation. As epsilon goes to 0, what does 1 minus epsilon go to? 1. 1 minus epsilon cubed, what does that go to? As epsilon goes to 0. 1. 1 minus epsilon to the 5th, what does that go to? 1. And so at the end of the day, when the dust settles, we are left with pi over 4 is 1 minus a third plus a 5th minus a 7th plus a 9th minus an 11th, yada, yada, yada. And that's a formula for pi. This is a numerical formula for pi. In terms of how good it is, it sucks relative to a lot of better formulas. But it's a formula. It gives you an exact value for pi. And if you want a certain accuracy, you can calculate what the error will be. Okay, any questions on what we've done? So we've now proven some of the fundamental things that we really need for this course. We've proven the area of the circle of radius 1 is pi, its perimeter is 2 pi. We have some idea of what the value of pi is. We were able to review the geometric series. We will see that a lot more when we get to the last unit of the course. We talked about when can you justify interchanging, integration. You need the double integral or integral sum of the absolute value to be finite. We talked about limits and how careful you have to be with limits. But if you know the limit exists, then you can take one special path and evaluate it. And so if we are willing to say that a circle has an area, if we're willing to say a circle has a perimeter, then we're fine. And we can just take those special paths coming from the regular inbox. Okay, so I want to just open up the rest of the class to just any questions you want. If not, I have some problems prepared. So is there anything in particular people want? Yes? I'm sorry? Level sets, sure. So the level set of a function is all inputs. So level set of height C of a function is all inputs that output to C. So for example, maybe I give you Z is a function of xy, and let's say that is the square root of 1 minus x squared minus y squared. Okay. This is not a completely random shape. It's a sphere, not quite a sphere. Half a sphere, a hemisphere. Yes, question?
How do you know it's a hemisphere?
Because z is always going to be positive. And so if I look at z squared, that would be z squared would equal 1 minus x squared minus y squared. So x squared plus y squared plus z squared is 1. So this is just going to be the top half of a unit sphere. And so if I want to find the level sets, I want all x and y such that f of xy equals c. So there are some values of c that should be very easy. So I want to solve c equals the square root of 1 minus x squared minus y squared. If c is less than 0, what points work? Do any points work? No. No solutions. The square root of 1 minus x squared minus y squared is always greater than or equal to 0. So if c equals 0, there's no solutions. If c equals 0, what's the solution? What's the only point that would give us c equals 0? Or are there more than one point? I'm sorry? Not x squared minus y squared, x squared. It's all points x squared plus y squared equals 1. So it's a circle of radius 1 centered at 0, 0. So when c equals 0, it's just the great circle. If c equals say some number in 0, 1. Well, if c is some number between 0, 1, I would get, c squared is 1 minus x squared minus y squared. I would get x squared plus y squared is 1 minus c squared. This would be a circle of radius the square root of 1 minus c squared. Circle of radius 1 minus c squared square root centered at 0, 0. So the goal is I just need to find all the points x and y that satisfy this value, that output to c. Why do you think I stopped at 1? Why didn't I allow c to be maybe 2 or 3? I'm sorry? Well, so if we tried to do that over here, we would actually get x squared plus y squared is 1 minus 4. There'll be no solutions. And so you can clearly see that if we took c to be too large, there'll be no solutions. If you look at it geometrically, however, once c is greater than 1, you're above this hemisphere. So if c is greater than 1, no solutions. So the level set of the hemisphere, if you think about it, they're going to be circles parallel to the xy axis. When c equals 0, it's the great circle, it's the equator. When c equals 1, it's the North Pole. For intermediate ones, it's your different, is it longitude that gives you how high you are? Okay, it's your different longitude lines. So, yes? It'll be all xy such that f of xy equals c. So we're just trying to find all x and y that equals c. So I can give you more complicated functions than this, but it all comes down to, can you determine which inputs go to the same output? Is this calculus? No, this is algebra. Where do we use level sets in calculus? We use them in Lagrange multipliers. We had our constraint. We were forced to live on a level set g of x, y equals c. We saw that it was extremely useful to have the notation and the language of a level set. But the actual analysis of the level sets is algebra. Any other questions? If not, I'll do a Lagrange multiplier. Yes? Okay, so that'll lead into a Lagrange multiplier problem. So we want to do optimization in several variables. So there's two things you have to consider. You have to consider interior points, and you have to consider boundary points. So if you want to optimize internally, what must be true for an internal maxima or minimum? The gradient is 0. So optimization. So internal point, the gradient vector is 0. And boundary, you need grad f is a multiple of grad g, where g of say xy is your constraint. The level set we were talking about just a moment ago. So let's do one in practice. So you have the ellipse x squared plus xy plus y squared equals 3. Find points closest and furthest to the origin. So I'm going to do this a little bit fast. I'll do a bad drawing. So when I was doing this in the 9 a.m. section, the first thing I noticed was I was trying to find a couple of points that were on it. And if you take x equals 1 and y equals 1, you get 1 plus 1 plus 1 is 3. If you take x and y to be negative 1, you get 1 plus 1 plus 1 equals 3. So the ellipse definitely goes through those 2 points. That tells you that 0 is going to be somewhere in the interior of the ellipse. It turns out I got lucky. This is actually poorly drawn. It's actually more like this. This is not the major axis, this is actually the minor axis. What makes this problem hard is this is not the format of the ellipse you're used to. You're used to ellipses that align with the coordinate axes. This one is not. Right, well, if I have some general point xy, and I want to find out where is it closest to the origin, what function should I look at? Should I look at the distance function? Yes. I should look at the distance squared. It gets rid of the square roots. So rather than trying to minimize, find the max and the min of f of xy is x squared plus y squared, subject to x squared plus xy plus 3, I'm sorry, x squared plus y squared, that's my g of xy, and that should be 3. All right, so the first thing we want to do now to do the boundary maxima is we do the calculus. We want the gradient of f, which is just 2x, 2y. We want the gradient of g. So I take this, I get 2x plus y, x plus 2y. And now we get our constraints. So we get 2x equals lambda 2x plus y. 2y equals lambda of x plus 2y. And what's the last constraint we have to remember? X squared plus xy plus y squared equals 3. We have to remember that constraint. Okay, so we have 3 equations. We have 3 unknowns. So there's at least a chance that we are able to solve things. Okay? How would you like to do the algebra first? What would you like to try first?
What lambda is.
Okay.
You can set it equal to each other.
So we could set these 2 equal to each other?
Yeah, if we solve for lambda.
Okay, so how would that help us solve for lambda?
Assuming that lambda is the second order.
There's a way to eliminate lambda. How could we eliminate lambda? Divide. Now, if we divide, we have to weigh maybe x or y is 0. So let's just break this up into cases. I would much rather have more candidates to check than spend more time thinking about how to do the math correctly. So let's do, case 1, x equals 0. Well, if x equals 0, what does y have to be? y has to be plus or minus square root of 3. So our points are going to be 0 plus or minus square root of 3, and their f value is going to be 3. So if you have a couple of extra points to check, it's not a big deal. Case 2, y equals 0. And then in this case, you get x is plus or minus square root of 3. The points are now going to be plus or minus root 3 and 0. And the f value is again going to be 3. So the general principle here is that it's sometimes a lot easier to do more checks than to be very careful in the analysis. I'd love to divide the first equation by the second, because that will cancel the lambda. But I can't do that if y equals 0. So break it up into cases. In one case, y equals 0. All right, but then I can resolve that immediately. And then in the other case, y is not 0. And if y is not 0, I can divide. So now, if we do equation 1 divided by equation 2, what do we get? We get x over y is equal to 2x plus y over x plus 2y. What would you like to do to these fractions? Yeah, cross multiply. So when we move this over, we'll get x squared plus 2xy is 2xy plus y squared. Life is good, right? The 2xy's cancel, and you get x squared equals y squared. So you get x is plus or minus y. So that gives us a few more candidates. Well, let's finish it. So now, if x equals y, now we go back into our last equation, x squared plus xy plus y squared equals 3. And then we would get 3x squared equals 3, so we would get x equals plus or minus 1. So the points are going to be 1, 1, and negative 1, negative 1. So if x equals y, those are the points that we get. And what will their f value be? The f value will be 2. All right. That already tells us these points can't be the closest. They could be the furthest, but they can't be the closest. All right, this was if x equals y. If x equals negative y, we now get x squared minus x squared plus x squared equals 3. So this gives us x squared equals 3. So the points are the square root of 3, negative square root of 3, or negative square root of 3 and square root of 3. And their f value is 6. And that's enough to tell us now which points are closest, which points are furthest. The 1, 1, negative 1, negative 1, they're the closest. The negative root 3, root 3, root 3, negative root 3, they're the furthest. I drew the ellipse the wrong way. The ellipse is really more like this. And these will be the points, negative 1, negative 1, 1, 1. Here will be the point square root of 3, negative square root of 3, and this will be the point negative square root of 3, square root of 3. So, if you understand the algebra of how to draw ellipses, you actually don't need to do the calculus for this problem. I like this because now I can just quickly check and see what's going on. But we can see our candidate points, and we checked a few points we didn't need to. But it was so little work to check them, and it allowed us to do the division that it's worthwhile. We technically never needed to look at the point when x equals 0, because we only want to divide 1 by 2. If x equals 0, not a big deal. If x equals 0, who cares? It was really, we didn't want y to be 0 because we were dividing 1 by 2. So you could have made it a little bit faster. All right, I will send emails in a little bit as to where I will be and when today.